The combustion engine. I'm sure we're all familiar with it, whether it be from a car, a boat, a plane, whatever. There's one thing they all have in common. They're all made of metal. But just like imagine if you could just like make one, like yourself, like on your 3D printer, and it wouldn't take like 2 years. Thankfully, I've already thought of this. And I think the thing is, just to get it running, all I need to really do is, you know, just kind of... Okay, I think it's time for me to face facts. This engine is just never going to work. Even if it were to fire, like, reliably, the problem is it's just such a small displacement, I don't think it even has enough power to, you know, idle properly. What I think I need to do is actually just start over from the beginning, because one, it's been a long time since I made a video on that engine, two, it's just not gonna work, and three, I looked like complete shit in that video. It's not even that hard, is it, you know, to make an engine? Just suck, squeeze, bang, blow. Like, what's the big wrong? You see, well, the basic premises of how an engine works isn't that complicated. It's extremely intricate when you get into the actual practice of the theory, on top of making one actually out of 3D printed plastic as well. To make a working engine, I have to overcome 3 different things. I have to overcome compression, I have to give it a good ignition system, and the last, and trust me, not least, is a good fueling system. Now, the first step in developing what is essentially a plastic bomb is actually to develop enough compression. And to do this, well, I kind of need an engine first. In case it wasn't obvious, I'm a massive hypocrite, and I decided to actually go with a steel crankshaft for this engine instead of a 3D printed one. When I was making it, I also put some counterweights on it, so it should actually, you know, give it some nice balance. If you've got a key now, you've probably noticed that this is actually just a modified version of my 3D printed VTEC engine. Well, kind of. The only thing it really shares the same is the stroke length. The bore is actually stepped up and I've just modified the whole rest of the engine. But before we can even get to thinking about compression, there's one super important thing that all Subaru owners dread: the head gasket. When I was in the 9th grade, our teacher actually made us hand in all of our assignments in these sort of duotangs here, which no other teacher has ever made me do. So it ended up with me just buying a whole bunch of these and then literally never using them again. In all seriousness though, this is actually the perfect material to make a head gasket out of, mainly because it's made out of this sort of like cardstock type paper, which tends to be fairly compressible, and that's exactly what you're looking for when you want to make a head gasket. To make sure that this is going to work well, I wanted to start by making a 3-ply gasket, and essentially to do that, all you do is just cut out 3 different shapes. Should be an arts and crafts YouTuber. This is so much easier. Yeah, Subaru better listen up. I think I just discovered the new meta for head gaskets, to be honest. And then glue them together with some silicone. Silicone is also great too because it's also compressible, so by having this sort of sandwich of all these little bits and pieces, under compression it should have a lot of, you know, deformation, which is kind of what we're looking for to fill in any discrepancies in the engine head. Okay, so all of this stuff pretty much just needs to cure now, the JB Weld and the silicone, and until then, I'm sweaty, I'm gross, I'm hungry, so I'm gonna get something to eat, and I'll come back to you when this is all finished. What's up? This is me in editing because I forgot to record a couple of things. One of the first things I did after all the JB Weld cured was I actually JB Welded a hub onto the crankshaft. And the purpose of this hub is basically just so I can bolt on a flywheel to it and also the starting tool as well. Now for the actual compression test itself, all I really did was just slip an O-ring onto the piston, and then I put a butt of oil on the cylinder wall and the piston as well. It is also worth mentioning that this has a 1:6 compression ratio, which basically means the volume of the cylinder at the bottom of its stroke will be compressed 6 times as the piston goes to the top of its stroke. This is pretty typical for lawnmower engines. It basically is a good combination of power, but also it makes it really easy to start because there's not that much resistance on the compression stroke. After that, it was just a matter of bolting the head onto the head gasket, and now we can do a compression test.
My engine is leaking.
To my severe incredulity, the engine had some seriously bad leaks. So bad that when I turned it over, the piston generated literally no resistance whatsoever. I could chalk this up to the fact that I stole the VTEC engine's valves verbatim and used it in this engine, but just to make sure, I actually put some water around the valves themselves, and sure enough, yes, it was leaking from there too. Yeah, that's probably... interesting. Now, because I'm a super genius, I discovered that these flaws were actually really easy to fix, and went ahead working on the Mark II version of this engine's head. So I was working on this new head, and, I was like, damn, these holes are kind of undersized. I take a drill, and I'm like, I'm just gonna drill them out a little to help it out, but, damn! That's not gonna work. I am great at wasting time. One of the big issues I discovered with the last head probably stemmed from the fact that when I JV welded the copper pipes in, I didn't even bother to clean them, nor did I bother to even sand them whatsoever. To fix this, I simply just roughed up the surfaces and I cleaned it with alcohol before JV welding it in. Instead of just relying on the TPU valves resting against the copper pipes themselves, I figured it was actually going to be a lot better if I just replaced the sort of valve seats with rubber O-rings. To make sure that this is going to make a really good seal as well, I actually heated them up and sort of pressed them in. So it's sort of like melting in the profile of the O-ring into the TPU valve. You could think of this as like a type of lapping, I guess. It was really weird. I was out driving and then these like white bits just like fell out from the bottom of the engine. I don't know what they are, but they seem to fit really well where the spark plug should go, so that's exactly what I'm going to do. Not very long after I JV welded the valves onto the stems, I really wanted to see just how much compression we could get out of this, even if nothing had fully dried. So I really quickly cut out a gasket, slapped everything together, and really wanted to see how this would work. Okay, I just spent like the last 3 days of my life trying to perfect this head, and I think I have it down pat. Hold on. Wow. That's crazy. Okay. It's alarmingly hard to turn it. I think it has about like a 6-to-1 compression ratio, but it clearly is working really well. Great, so it seems like we have a lot of compression. But how much compression? I do not own one of those really fancy, sparkly compression testers, so I'm gonna have to come up with my own solution. I decided to actually just 3D print a blank head and put it on the top of the engine. The thing with this blank head, however, is that it actually shares not only the same compression ratio as the regular head itself, but on the top, there's a very gorgeous thread pattern fit just for a pressure gauge that I can screw into it, and then we can just turn it over by hand to read how much pressure we're getting. I felt like this had a little bit too much compression, and I wanted to see what would happen if I made one that was actually shaved off a bit with sort of a flat top. Okay, so I think the reason why we got the results that we did were the flat piston actually had better compression, which is ironic because the other piston should give us more compression. Maybe this is because A, I reused the gasket, which is a big no-no, or B, the fact that it's compressing so much, it's causing some blow-by around the ring. But I think that this should work just enough, but I'm not 100% sure, so I guess we'll just have to see what happens. And with that, my friends, we have now just conquered the compression crisis. Before I start talking about the new engine's ignition system, we got to talk about the old engine's ignition system and kind of just how it's not very good. What I tried to do was sort of make a contact brake ignition system, but the problem with it is that one, it wasn't reliable. It just kind of worked whenever it felt like, I guess. And that was assuming that it was working, because that brings me to my second point. It didn't work just at all sometimes. Later in the testing, I was pretty sure that we had lost the ignition. I don't know why. It would just go periods where it just wouldn't deliver any spark whatsoever. Now these were serious problems and I really needed to fix them. But that's when I remembered something about the ubiquitous light switch. They actually have contact breakers inside of them. Much similar to the ones that you'd find in an old engine actually. And because of this, what I did is I tore apart a really old one and decided to repurpose them as my contact breakers for this engine. But how is this actually going to work? Well, let me explain. This is a circuit diagram. You can see that when the contact breakers are closed, the current flows, but nothing happens. Once the contacts are broken, the current stops flowing and a spark is delivered to the spark plug. If you time the breaking of the contacts correctly, you can use this on an engine. But why does it deliver spark when the contacts are broken? This is a coil. Now this is inside a coil. There is actually two coils, a primary coil and a secondary coil. When current is applied to the primary coil, it creates a magnetic field around the secondary coil. But if the flow of current is broken, this magnetic field collapses inwards and induces a current on the secondary coil. Because the secondary coil has approximately 3,700 times as many windings, it multiplies the voltage of the primary coil by 3,700 times. meaning 12 volts into the primary coil should deliver almost 45,000 volts to the spark plug. If you like what I'm talking about, want a free and easy way to learn more about it, then maybe you'd be interested in today's sponsor, Brilliant. Brilliant is great for learning more about practical and theoretical areas of math and science, just like you've seen me do here. The genius of Brilliant lies in its fun and interactive lessons. Whether you're starting out from the basics of engineering or going through advanced level calculus, Brilliant is there to make sure that you're never going to get stuck with helpful hints and step-by-step solutions to really difficult problems. In case you're worried about getting bored learning the exact same stuff over and over again, Brilliant freshens things up by adding new and intuitive lessons every month. These lessons will help broaden your field of knowledge and also keep things interesting. Being an engineering student, I actually really like Brilliant because it helps me gain a tangible understanding of my stuff from my school courses, but also stuff that I do in my project videos. In this example, the molecules are actually represented as marbles, and you can see that the pressure is actually determined by the surface area of the container, or in the case of an engine, it's determined by the surface area of the piston. Now, if you're interested, you can get signed up for a free 30-day trial, but it doesn't end there. The first 200 of you to sign up can actually get 20% off of an annual plan by visiting brilliant.org/CamdenBowen. Thank you once again, Brilliant, for sponsoring this video, but now let's get back to it. So if there's anything you could take away from that, the whole point of a contact brake ignition system is it only makes spark when the contacts are broken. So in order to do this, what I did is I added a funny looking cam at the end of the camshaft, and this is entirely dedicated just to delivering spark. Now when the camshaft rolls over, what it will do is it will actually lift up the contacts and break them at the right time. But just in case the timing is off, you can actually rotate the whole assembly by a couple degrees both ways. This is to either advance the spark or delay it. But is this system really going to ignite anything at all? Let's find out. It did nothing. Yeah, so before I could actually get this to work, all my neighbors decided to come outside. So I actually went back inside before I can get in trouble for essentially constructing a bomb. Even though nothing happened, I was just so determined to see any kind of result, I figured, yes, maybe if it's under compression, it might work a little better. Oh, that's cool. With the setback of my tool breaking, I figured I could at least turn it over by hand. Nope. Yeah, so this trash can basically stopped delivering spark, again for some reason. If anybody wants my channel, I will be posting it in the description for sale at a bidding price starting for $3. By this point, I was feeling defeated. But then I decided to do some investigating on the spark plugs themselves. Now the one I had been using had a really close gap, but the spark looked relatively fine, I guess. I then compared it to another one that was the same sort of size as that one and noticed that it had a lot larger gap, which is actually what I'm looking for, but it had a really weak, just bad spark, like it was just garbage. At this point I was just like, dude, what the heck is going on? To make sure that the weak spark was actually caused by the fact that these are old and trash spark plugs, I actually went out into the wilderness to go and buy a new one. Spark plug obtained. But as it turns out, this whole time I've been a fool because the answer has been right in front of me. Don't use any spark plugs at all. If I actually just use 2 screws as electrodes, you can see that it not only delivers a really strong spark, but it also does it across a fairly large gap too. Just to convince myself that this actually is the better solution, I decided to put it all back together into that bottle test and then try it again. Now I could make a new head, I could, but out of laziness and also convenience, I figured it was actually smarter to just plug the old spark plug hole, drill 2 new holes out for the electrodes, and then just kind of plug everything with JB Weld. Now I wanted to make sure that this was really going to work, so I put everything back outside, made a new crank tool, and then went and gave it a shot. For a while, I was starting to lose hope, but that was before this happened. No way. That was a lot of power, and it destroyed that JV weld. So to make sure that this doesn't happen again, I actually welded on a little plate that I can use as a hub onto the crankshaft with the most wretched, disgusting, just hideous welds I have ever made. But to be honest, it's actually strong enough, and it's going to allow us to move on to our next step. To be completely honest, thus far with this engine, I haven't really accomplished anything out of uncharted territory. I mean, in the last engine, I was able to accomplish compression. I was also able to accomplish an ignition system. Oh my... And I did get it to fire a couple times as well. But that one thing, just that one thing that has haunted me for almost 2 years now, the fuel. Here's where you get to a little fork in the road when it comes to the fuel. You either have liquid options or you have gas options. Now, liquid options make sense because you can just make a carburetor and then the engine will just draw in the fuel as it needs, and then you can dial it in yourself. That's assuming that the gasoline or the alcohol that I plan on using doesn't just obliterate all the different plastics, and that's kind of not very good. But this isn't the case when you use something like butane. If you actually use butane, you can put as much in the engine as you want, and it'll just kick out what it doesn't burn. It's not going to mix in with plastic or the oil and ruin everything. After weighing the pros and cons for a whole of like 5 minutes, I decided to go with the butane again. But I still need to think of a way to put it in the engine. External fuel injection. Much like how I was blowing butane into the engine with a little torch, I plan to do this on a much larger scale. But here's the catch. Butane by itself is completely useless. It's garbage. You can see if I take straight butane and then just light it off, it makes kind of a large yellow flame because it's not mixing with any of the air. But when I pass it through this funny looking tool called a Venturi, you can see that when it exits, it's creating a very sharp, hot blue flame. Sharp. Why would I say sharp? Now the difference is inside of a Venturi, there's a little nozzle that the gas is jetted through. And when it's jetted through that nozzle, it causes surrounding air to be drawn in and mixed with the butane on the way out as it's expelling through the little tube. Now this tool is what I'm going to use to blow fuel into the engine. All I've had to do to make sure that the engine can receive fuel from said Venturi is basically just prop it up on the side. It's a really simple system. All it really comprises of is just the Venturi just dumping fuel into the engine, and hopefully this is going to work. But it's missing one key component, something so important and so unforgettable: the velocity stack. I love velocity stacks. They add such a nice sound to every engine they're on. But they also serve a very important purpose as well. Now, if you just try to use a regular piece of pipe as an intake, you'll find that there's actually a bit of a restriction. And this is because the surrounding air, when it's trying to enter, do a bit of a 90-degree bend on its way in. So it actually creates a smaller area where the air can actually enter versus the total size of the pipe. But that's not the case with the velocity stack. And this is because the velocity stack almost acts a little bit like a funnel, where it sort of funnels air in and it gives it a really smooth surface that it can just kind of run in really easily. By having the velocity stack, I'm hoping that this will help the engine breathe a little bit better and get more air and fuel into it, which will up our chances of it running. Also, it just looks cool. Remarkably, it seems like the fuel system is probably the easiest thing about this whole engine. I mean, the compression was a bit of a challenge.
It's leaking.
The ignition was a far more bigger challenge. But the fuel system seems pretty straightforward. But there's only one way to find out if it's going to work. To give ourselves the best shot, I went ahead and I dialed in the engine's timing, set up the ignition timing, and then to preserve the engine for a little bit longer, I had decided to add a bit of oil to it, which the engine immediately just spewed out anyways. But when the remaining oil sat at the bottom of the crankcase, I was able to get it to stir around and get all over the place, and this should give us the best shot during our test. To start the test, I first started by delivering fuel to the engine using the Venturi system that I had made. Now, while I was turning it over, I was actually fairly confident in the design of this because it didn't feel like it was immediately going to explode. Now, when I was cranking it over, it really wasn't doing a whole lot until it would spin down, and that's when we were getting, some pops and bangs, and this was giving me hope. Just to leave no stone unturned, I decided to actually turn it a little bit slower, with no real result. However, not was all smooth sailing, because I for some reason forgot that when butane evaporates, it gets really cold. And when butane gets really cold, it stops evaporating. Before I went and tried anything else, I wiped both the engine and myself down. It's almost like leaving a massive gaping hole inside of the crankcase was not a good idea. Now earlier I had really decent results using just the regular butane torch, probably the best results yet, so I actually went back to using that to try it again. Nope. To see if anything would happen, I decided to turn it over again, with my hand. This might like break my wrist. That's okay. Now thankfully this is an engine that I designed, because if it were anything else, I'd probably be out of a finger. I've had the severe and continuous lapse in my judgment thinking that butane was going to work. Just like the hypocrite I am, I'm leaning towards more of kind of a liquid solution to this, maybe some kind of carburetor or a fuel injector. Again, I'm not 100% sure. But basically, like, the whole butane system is just trash. Anyways, I'm gonna leave this here, and then I'll see if I can figure out something in the future. So the engine, like, didn't work. I noticed after the test the engine sort of lost a lot of compression, but it sounded like it was through blow-by, not through the engine's head. So I took everything apart to have a quick look. Hey guys, welcome back to another episode of What's Inside. What's inside my soul? Camshafts looks really good actually. Sure enough, the engine's head looked immaculate. Impressively, the inside of the head is like completely dry. Epic. But when you looked at the cylinder wall, there was a lot of gouging on the one side, and this is probably where that piston slap came from. It's got some piston slap, which it definitely didn't have before. Am I disappointed? You see, one of the biggest problems is whenever I test stuff like this, if it doesn't work on the first try, when I'm done after, it's not a matter of just fixing what didn't work. I end up having to rebuild half the engine because usually something gets destroyed in the process. But the thing is though, I still view this engine as a really big success. I mean, in terms of quality, it's probably my most refined engine yet. Before I destroyed it, essentially, it had a lot of really smooth running parts, and everything was like super low tolerance. It really does make this just look kind of like a Happy Meal toy. Not only that, I'm super satisfied with the overall just like perfect seal of the design, and I think I can actually utilize this in my future air engines as well. So stay tuned for that. I'm not entirely ready to throw in the towel yet. I think that I will probably return to this again in the future when I have some time set aside for it. But I think for now, I'm fairly satisfied with these results, and I hope you are too, because that's it for today. Thank you for watching this video, and thank you guys so much for all the support you've been giving me on the last few videos as well. Anyways, that's it for today. Peace, guys. Yeah.
That didn't hurt.
What?